Hey, this is Mr. Ward. I'm going to talk to you a little bit about Chapter 3, Congruent Triangles. I'm going to start off with a short video about Chapter 3, Section 1. I'm going to lay out three basic ways to prove triangles are congruent. There's more than just these three. What it means to have congruent triangles and what included angles and included sides are. So, to be congruent, two triangles to be congruent, all their corresponding parts need to be congruent. So if these two triangles are congruent, and I know that A is congruent to D, angle A is congruent to D, angle B is congruent to angle E, and angle C is congruent to angle F, and I also know that AB and DE are congruent, and AC and DF are congruent, and BC and EF are congruent, then I have just identified all the corresponding parts of those triangles that are congruent. And then we want to name the triangles in the order that we named it. So if I name this triangle ABC and I'm declaring it's congruent to this one, I want to name this one DEF. Keep them in order. So assuming D and A are corresponding parts and B and E are corresponding parts, that means they are not just in the order that they show up, but they are congruent. So those corresponding parts need to be named in order. So here we give you two congruent triangles. Triangle ABC is congruent to triangle DEF. And we mean all the following. We mean that triangle ABC has the same size and shape. The size is defined by the sides, and the shape is defined by the angles and their relationship amongst each other. So you could take this triangle and plop it right on top of that triangle, and they would be exactly on top of each other, and they would be congruent. And so we can see the little image of this where they're plopping ABC onto DEF, and so ABC and DEF are being plopped on top of each other, and all their pairs of corresponding parts are congruent. So we have this symbol, which means if then, and there's the double arrow symbol, which means that the statement is reversible. That's kind of useful, by the way, down the road. You can use it as a shorthand. Now, included angles and included sides. So there's this use of this language of included angles and included sides. So if I am talking about included angles, the included angle J is included between GJ and HJ. It is the angle that is in between those two sides. Angle H is not in between those two sides unambiguously, because angle H and angle G are both between it. We want to look at the one that is most definitively between those two sides, and that's J. So the included angle J is included between sides GJ and HJ. The included side GJ is included between the angles G and J. So it's the one that's in between. Included means it's going to be the most in between thing. Okay, then we lay out three different ways to prove triangles are congruent. Side, side, side is one, where this side and this side, this little mark means this side, CB and FE are congruent. And this triple mark means that AC and DF are congruent, and this double mark means AB and DE are congruent. These two have the same mark. So we could say side, side, side. All three sides are congruent to their corresponding sides. So there's a fancy way of saying it, but we're going to usually say side, side, side. If there exists a correspondence between the vertices of two triangles such that three sides of one triangle are congruent respectively to the corresponding sides of the second triangle, all that's saying is these three sides are congruent to these three sides, and therefore those two triangles are congruent. And then there are two others. One is called side angle side, and what that means is if two sides and the included angle, S stands for side, A stands for angle, these two sides and the included angle, the angle that's in between them, are congruent. If you can prove that, then you can prove that the triangles are congruent. And additionally, if you have two angles and a side in between them, you can prove that those triangles are congruent as well. This is called angle side angle, and it's named ASA because it is literally angle and the side between the angles and the next angle. That would prove them congruent. Three angles being congruent does not prove congruence. We'll talk about angle, angle, side, and side, side angle, and as configurations, and as well as one called hypotenuse leg later. But here are problems. I'm going to take a look at a couple of the even ones right now. Number 2 here, if I wanted to prove side, angle, side for these two triangles, I have a side and an angle. I'm going to need another side. So that's going to, I'll pick GJ and OM. If I could prove that, then I could prove side, angle, side, and prove congruence of the triangles. If I wanted to prove angle, side, angle, then I'm going to need to get angle H and angle K, prove that they're congruent, because then this side is the included side between H and G. So I need to prove angle H and angle K are congruent. Now let's look at the actual problems in the problem set. So those are sample problems. You'll definitely want to look through those sample problems. Let's look at a couple from the even ones. So here we have, using tick marks for each pair of triangles, name the method side, 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 angle, side, or angle, side, angle, if any, that will prove the triangles are congruent. So here we have these two triangles. They have a side and an angle and a side. And a side and an angle and a side that are congruent. So side, angle, side, SAS. These two triangles have a side and an angle. They have a side and an angle. That is none of these options. So B, we do not have enough information to prove that they are congruent based on what we have. Later on, we'll discover that side, angle, side can produce two different triangles. It only works if the angle is a right angle. More on that later. Here we have an angle and an angle and a side, angle and an angle and a side. We actually no, we don't have any sides. We have angle, 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 angle. So we cannot prove that these triangles are congruent. These triangles we can prove are similar. That means that they can be scaled up and down and have the same shape, but not the same size. They would produce proportional side relationships. Here we have triangle ABD and triangle AEC. So ABD and AEC. So we know that this side is congruent and this side is congruent. All right. Do we have, and we know angle B and angle E are congruent. We know angle D and C. So this triangle here would be congruent with this triangle here by angle, side, angle. Angle, side, angle. So these are overlapping triangles, which is a little harder to see. Sometimes it's useful to color code or draw them. You've seen 6 in a do now earlier. I'll talk about number 4 here. We have angle 1 and angle 2 are congruent. We have EF and HF are congruent. We need to prove whether triangle EFJ and HFG, notice they are naming each other in the same order, okay, are congruent. And the thing we need is, we've got a side and we got an angle, but these are vertical angles. And in the last chapter, we determined that these two angles are congruent too. So we've got angle, side, angle. I'm going to go on to number 10. Number 10 is, we've got O is the midpoint of AY, and O is also the midpoint of ZX, okay? And if it's the midpoint, then this side and this side are congruent, this side and this side are congruent, and the vertical angles are congruent, so we can prove these two triangles are congruent by side, angle, side, side, angle, side. We know that YO and AO are congruent. We know that ZO and XO are congruent. We actually don't have enough information to know that that YO and XO are congruent because we haven't been told that O is the center of the circle. It might be, but we don't have that information. But we do have enough information to know that this side and this side are congruent, this side and this side are congruent, and we can prove that these two angles are congruent by vertical. So side, angle, side will prove that. All right, I'm going to stop, and I hope that was